Hello friends, welcome to another tutorial in analog electronics. In this tutorial we'll talk about a special multi-stage amplifier which is known as Darlington Pair, and we'll see the characteristics of this multi-stage amplifier. It's also known as super beta amplifier. If this is something that interests you, then please keep watching. When we talk about Darlington amplifier or Darlington pair, it's an arrangement of two common collector BJTs arranged in this manner. Now please understand, we have two transistors Q1 and Q2 whose collectors are common. Now when collectors are common, we are left with the option of giving input at bases and taking output from the emitter. Now please understand, this transistor might look something like this from the outside, but the internal structure of this transistor will have two BJTs, one followed by the other. Because of this special arrangement of these two BJTs in such a way, this transistor will act as a super beta amplifier, which means that it is going to be a current amplifier of a very high magnitude, and we're going to see that how that happens. I have written down some key points for Darlington pair. That two CC BJTs are used. Emitter of Q1 is connected to the base of Q2, and it's known as super beta amplifier. The gain is beta 1 into beta 2. The overall gain, the current gain, is very high. Let's see how that effectively comes into play. Let's first find out the current gain. The current gain here can be thought of as IE2 upon IB1. The current here at the output is IE2, let us say, and the current at the input is IB1. So the overall current gain of Darlington pair will be AI, which is IE2 upon IB1. From this figure we know that IE1 is equal to IB2. This current IE1 is directly being fed to the base of the second transistor, so IE1 will be equivalent to IB2, and IE is equivalent to IB plus IC. We know this from the basics of transistors, and IC is beta times IB, so we can say IE is 1 plus beta times IB. This is a well-known relation, and if beta is greater than 1, then I can approximate my IE to be equivalent to beta times IB. So this is the first approximation that we take, and IE1 over here at this point is beta times IB1, and IE2 is beta 2 into IB2, and IB2 is substituted as IE1, and IE1 is further substituted as beta 1 into IB1. So putting this value of X in this equation of current gain, we get the current gain to be equivalent to beta 1 into beta 2. And if, let us say, beta 1 is 100, beta 2 is 150, then we'll have 15000. So much of current gain. So that is why it is known as a super beta amplifier with a super high current gain. This was an easy approximate analysis of the Darlington pair, taking into account the simplicity of the structure of this amplifier. Now let's discuss a few more key points. again I mentioned if beta 1 is equal to beta 2 is equal to beta, then the current gain becomes beta square. These are the few key points that I want to mention. The reduced size of this amplifier is an advantage because of common collector condensed circuit. It looks like one BJT. And the disadvantage of this circuit is that there's going to be some VBE here and there's going to be some VBE here, and the total VBE of this equivalent transistor is going to be the sum of both the VBEs. So if we are talking about silicon BJT which has VBE of 0.7 volt, the total VBE of Darlington pair transistor is going to be 1.4 volts, which is a disadvantage nevertheless. Now let's get into details of the AC analysis of this Darlington pair, where we can find the current gain, the voltage gain, the input impedance and output impedance. In order to find all these parameters, let's consider that R pi for each of these transistors can be substituted as HIE, beta can be substituted as HFE, and GMR pi will be substituted as beta times IB. So this Darlington pair arrangement can be transformed into its equivalent circuit like this, where this portion is transistor 1, and we know that every transistor has HIE and a current source beta into IB1. So this is transistor 1 and this is transistor 2, and this transistor will also have its own HIE and current source, which is beta IB2. So if you can reduce this arrangement of Darlington pair into its equivalent AC circuit with HIE and beta IB, HIE and beta IB for both the BJTs, and finally we have RE as the load resistance. Voltage V0 is dropped here, RE is the load resistance, I0 is the output current. So reducing the transistor model, we get AI, this is AI, which will be I0 upon I input. The output current can be thought of as, if you consider this node, two currents are entering into this node. The first current is IB2 and the second current is beta times IB2. So I can say the output current is IB2 plus beta times IB2, and the input current is IB1, and this is IB1 by the way. Now what happens is, but we know that IB2, the current in this branch, is the sum of these two currents, because at this node these two currents are entering and this current is leaving. So IB2 is the sum of IB1, which is the input current, and beta times IB1. So I can substitute IB2 as IB1 plus beta times IB1, and substituting IB2 here, I get 1 plus beta IB1 plus beta times IB1 divided by IB1. So what I get is my current gain to be equivalent to 1 plus beta into 1 plus beta. If beta is very very large than 1, then I can ignore these ones, and again approximately my current gain comes out to be equivalent to beta square. So even if you solve this using this method, you'll get the same result. It's a super beta transistor with a humongous current gain. In order to find input impedance and output impedance, you need to remember few key points, that when we move from emitter to base, we multiply the resistance by 1 plus beta, and we move from base to emitter, we divide the resistance by 1 plus beta. So if I was to calculate the total impedance Z in, I can start from RE, and then as I move from emitter to base, I multiply it with 1 plus beta, and then my next impedance is this. I add this up, and when I move from emitter to base again, I do multiplication with 1 plus beta, and my final is this HIE. So this is the total impedance, input impedance. And if I ignore ones and HIEs, I can ignore 1 HIE, I get beta square RE to be the approximate input impedance. Very important result that you can commit to your memory. And finally, for the output impedance, you do the exact reverse tracking. You start from the top HIE and you move from base to emitter, so you divide it by 1 plus beta. Then you again find an impedance HIE, and then you move from base to emitter, so you divide by 1 plus beta, and finally you find RE, which is parallel to all this. And if you again approximate, neglecting ones and HIEs, this beta will get cancelled, you get RE approximation. And finally, to find the voltage gain, which is the ratio of V0 upon V input, so V0 is I0 into Z0, V in is II into Zi. So substituting the values, you'll get the answer to be equivalent to 1. And this is a very important result, that Darlington pair is used as a voltage buffer also. So it does not provide us any voltage gain, however the current gain is humongous. So these 4 results are very important, that the output impedance is approximately equivalent to RE, the input impedance is equivalent to beta square RE, the voltage gain is unity, and the current gain is beta square. So that's about it for the Darlington pair. It's a very important multi-stage amplifier, one of a kind, made from common collector, used for current amplifications. And I hope this tutorial was of help. If you liked the video, give it a thumbs up, consider subscribing to the channel, share this video as much as you can, spread the good word. I'll see you around in the next video. Take care, have a good day, good life, bye bye.